So our last learning unit in Gen Chem 2 is going to be on organic compounds. So we're going to focus on two main aspects of organic compounds. We're going to learn how to properly draw them, and then we're going to learn how to recognize functional groups that are present in organic compounds, because those functional groups are really what dictate physical properties and chemical reactivity. So again, we set this chapter and learning unit at the very end of general chemistry, even though it's kind of right in the middle of your textbook. And the main reason for that is so that we can kind of set you up to have this stuff freshest in your memory as you move into organic chemistry, for those of you who are moving on to this next full year course in our chemistry sequence. So I'm going to start out here by I'm not going to spend a lot of time on these slides, just highlighting some important concepts from previous chapters, and many of these are previous chapters in General Chemistry 1. So again, if you need a refresher on that, you can go back to the Blackboard content from Gen Chem 1. But always important to be able to kind of name chemical substances. And again, we have a cumulative final exam as well, so this is not just important for this chapter. But importantly for this chapter, since we're dealing with covalent compound, is sort of thinking about these binary covalent rules. So again, this was way back in chapter 2 from General Chemistry 1, where we learned how to name compounds. But again, we started thinking about the concepts of binary covalent compounds. And then towards the end of Gen Chem, and this is going to become a very important skill as we move forward in this chapter, is thinking about how we draw two-dimensional and then three-dimensional representations of our molecules. So we learned in chapter 10 about how to draw Lewis structures, so I'll have a brief review of that. And then it's important to think about the molecular shapes that these compounds have, because that shape is what really dictates structure, and structure is what affords function in many molecules. So again, just a real quick overview on these slides. All of these individual documents are up on Blackboard if you would like to download them, kind of have them for review. But we used this in chapter 10 as a way to think about electrons being glue, and again, making those bonds that hold atoms together. So when you're thinking about how to draw a proper Lewis structure, you have to make sure that you have the right number of electrons. So that has to do with looking at the number of valence electrons you have, making sure that nothing violates its octet rule, thinking about formal charges. So again, all these concepts from chapter 10. If you feel like you need a refresher, you can go back and look at that content from Gen Chem 1. Again, still content that's going to be important for a cumulative exam, but very important in this chapter to sort of move forward. I am going to spend a little bit of time on this slide, because this slide is sort of a really important slide to think about with building organic molecules. So most of the atoms that we're actually going to see in our organic molecules are going to be carbon, nitrogen, oxygen, and hydrogen. So what I have here on this little chart here is just a reminder that our periodic table is our best cheat sheet. So if you can envision your periodic table, or take a look at one if you have one next to you or in your textbook, and look and see that groups 4A, 5A, 6A, 7A are where we see carbon, nitrogen, oxygen, and then our halogens. And what we can do is we can use the periodic table to tell us by that group number how many valence electrons each of these species has. Remembering here that hydrogen only has one valence electron. Then when we draw electron dot diagrams for each of these, and again, always making sure we give electrons room, we can see that carbon with 4, 5, 6, and 7 electrons as we go through the rest of that series here. If we set them up so that they don't have to be paired unless they're required to, we can set up to see that carbon has 4 unpaired, nitrogen's 3 unpaired, oxygen's 2, fluorine is 1, and the same thing for hydrogen, 1 unpaired electron. And why this is important is that number of unpaired electrons, which corresponds to the number of valence electrons, tells us how many bonds these atoms like to have. So carbon likes to have 4 bonds. Nitrogen having 5 electrons, which means that there's 3 that are unpaired, likes to have 3 bonds. Oxygen having 2 unpaired electrons likes to have 2 bonds. And then halogens and hydrogen like to have 1 bond. Why this is really important is as we build larger molecules, covalent compounds tend to be much larger than we see for things that are inorganic or salt-based. So what we tend to see with these larger molecules is we have to think about where our pieces will be. And so when you have something that likes to have 4 bonds like carbon, we're going to see these as central pieces. We're going to see things with nitrogen or oxygen making 3 or 2 bonds tending to be more like, I like to think of these as bridging pieces. And then we're going to see things like halogens or particularly hydrogens being end pieces because they only form 1 bond. So if you sort of envision this in your brain, it'll help make sure that you don't draw incorrect Lewis structures. So here's just a bunch of different examples of some organic substances that are down here. Everything from, this is vinegar, this is acetic acid, but we can see that carbon here always obeys these rules. It's always going to have 4 lines, 4 bonds drawn around it. Sometimes it's 4 single bonds, sometimes it's 2 singles and 1 double. I don't have any examples here of triple bonds, but we can see anytime we have a nitrogen, nitrogen likes to have 3 bonds and 1 lone pair. We're going to see a little bit of an anomaly here. We'll actually talk about this guy when we do one of our practice problems, but there's actually 4 bonds there for that nitrogen, but what we've done is we've actually taken this lone pair of electrons and we've bonded it to a hydrogen atom, which gives that nitrogen a +1 formal charge. So that's why we see that. Oxygen, again, we see 2 flavors of oxygen here. Here's an oxygen kind of with 2 single bonds, and then we can see oxygen with a double bond. Okay, so we're going to see these patterns, and the quicker that you can recognize these patterns, the better you're going to be at making sure you can quickly draw accurate Lewis structures. And then we moved on in chapter 11 to sort of think about 3-dimensional structures, because remember, Lewis structures are really a 2-dimensional representation. Even though we might be implying some 3-dimensional nature to them, they're really on paper 2-dimensional flat structures. But we have to remember that we see things and molecules exist in 3 dimensions. And so that's where we started thinking about that Vesper model. So maybe you're getting a little twitchy here, sort of remembering all of these things with sp3, so hybridization. We talked about sort of the molecular shapes. We've got tetrahedral, we've got bent. We go on and we have larger molecules and we still kind of apply these same rules. And this is really important because molecular shape is what gives us structure. And structure is what really affords function with biological and larger organic molecules. So again, bigger molecules, no problem. We sort of had this same kind of a slide in Gen Chem 2 or Gen Chem 1 when we said, you know what, it doesn't matter if we start getting to bigger molecules that have more atoms. We just need to treat each individual central atom independently, and then we can figure out the hybridization around it. We can figure out the bond angles around it. It doesn't matter if we get bigger and bigger, we just kind of have to keep considering each piece separately. So again, we can get to big molecules like carbohydrate polymers, we can get to proteins, we can get to nucleic acids. So all kinds of really great biological molecules that really run our bodies are just the same, carbon, hydrogen, nitrogen, hydrogen atoms that are just made into much larger molecules. All right, so we are going to focus and we're going to build on carbon as a building block. So just kind of reviewing, and here we can see a little bit of that periodic table here. When we have carbon atoms, and remembering our octet rule, and carbon's in group 4A, meaning it has 4 valence electrons. Remember other things, we could easily make ionic substances with them because they could easily give up if we are over here in sort of the metal category of our periodic table and become cations, or they could take on and become anions if we're more in the non-metal or the right side of our periodic table. But when you have something like carbon that's right in the middle there, it really doesn't want to give up 4 or take on 4 electrons. So carbon shares electrons. We don't see ionic compounds with carbon. And that's because of where it exists in the periodic table, right? Those 4 valence electrons. But as we saw, it likes to form 4 bonds, and including bonds to other carbon atoms. So again, the ability to bond to itself allows us to create large molecules that are basically carbon at its core to kind of form these scaffolds for these large molecules. So building on this concept, when we introduce non-carbon and hydrogen atoms, we call these functional groups. And this is what our lecture on our second lecture in this chapter is going to be about, is thinking about functional groups. And so that's when we have groups of atoms that are bonded together in specific ways. We're going to learn about 15 functional groups. You have to be able to recognize what atoms are part of them and what their name is. So a little bit, I don't like memorization a lot, but sometimes we have to have a toolbox of knowledge. And so we're going to need to think about what these functional groups are. We're going to see a lot of them containing oxygen and nitrogen. Again, we call these heteroatoms. Hetero meaning different. Okay, different atoms than we normally will see with our carbon and hydrogen. So again, that's going to be the focus of our second lecture here in this learning unit. So when we draw these carbon skeletons, remembering the magic number of 4, each carbon atom is going to form or have a maximum of 4 bonds. Again, we can have 4 single, we can have 1 double and 2 singles, 1 triple and 1 single, lots of ways that we can sort of build carbon together. And again, that arrangement of carbon atoms is going to determine what we call the carbon skeleton. That's going to be kind of the building block of our molecule. Okay? One of the things that we have to remember is that if we're building things with just single bonds, we can rotate freely about those bonds. And so again, we can actually easily think about having different arrangements of atoms just by rotating about bonds. So we'll practice kind of seeing this, and we'll actually play with some models to practice it. One of the rules that we're going to have to make sure that we think about, because sometimes we're not actually going to be drawing in every single hydrogen atom. If we have carbon atoms that are bonded to other carbon atoms, we need to remember that any extra spaces are going to be filled up with hydrogen atoms such that every carbon will have 4 bonds. This will make sense as we go through and practice some problems, but I just kind of wanted to highlight that important piece. I'm going to talk about 2 different kinds of isomers, and I'm going to kind of highlight here when we see the word isomer. Iso means same, mer means part. So what we're really doing is saying we're going to have the same parts, we're going to have the same atoms, but we're actually just going to arrange them differently so we make different molecules. Okay? And so what we're going to have here is just an example here. Here's 4 carbon atoms that we can put together in a straight line. We can actually have 3 carbons in a straight line and then 1 carbon coming off the center. It has the same molecular formula, right? They're both going to be 4 carbons and then 10 hydrogens. But what's going to be different is how we arrange those carbon and hydrogen atoms. Now, we don't have a lot of options here because we're always going to be putting these carbon atoms in the middle. Hydrogen atoms are always going to be on the outside. So there's not a lot of options with this small molecule here. Don't worry about what these are named. We're not going to go through naming here. Even though it's part of your chapter, we're not going to discuss it in our Gen Chem sort of examination of this chapter. Will be a really important skill in organic chemistry. So what I want to highlight here is if we wanted to have this molecule, and again, if you were to imagine building this out of like Tinker Toys or Legos or whatever you want to think about sort of as a building tool, if you wanted to take this guy and make him into this guy, you'd actually have to disconnect there and then reconnect here. So that disconnection and reconnection is what defines a constitutional isomer. Okay, and I do want you to know these definitions. I do want you to be able to look at 2 different substances and tell me, are they constitutional isomers? Or, as we just talked about on our last slide, are they conformational isomers? I'm going to draw another molecule here just to kind of highlight here. If we were to imagine this guy and we were to draw him like this, it's going to look different. He's going to look like he's bent in half. I'm going to draw all these hydrogen atoms here. And you're going to see in a minute why we're going to learn a different way to draw molecules, because it takes so long to draw molecules all this way with all of this. Now, it might look like I drew something different, right? Because this molecule here is a straight line. This one is bent. But remember, all that I needed to do is sort of bend and rotate my bonds to get to this molecule. So these two are really the same molecule. They're not isomers of one another. They're identical. So some of the questions that you're likely to see related to concepts for this learning unit in this chapter are thinking about how would I classify these molecules? Are they the same, being conformational isomers? Are they different in being constitutional isomers? Okay, so we'll do some to practice with that with a problem in just a minute here. So again, different ways that we can represent structures is going to become a key skill in practicing in this first lecture. So I want to introduce kind of different ways that we think about representing structure. So you guys are used to what we call an expanded formula. That's drawing every single atom out, drawing every single bond out. Now, it gives us the most information. We clearly see everything that's going on, but it takes the longest to draw. So the skill that we're going to practice today is moving towards what we call a skeletal formula. And we're going to take this in stages. The first stage is saying, you know what, let's collapse some of our bonds. So we're not drawing all of those bonds out. And we call that a condensed formula. So you can see we've condensed these 3 carbon-hydrogen bonds to just be CH3. That saves us some time in writing, right? But what we're going to then move on to after that is say we're going to condense it even further because it's super quick to just draw a bunch of zigzag lines rather than drawing out every single atom. So not only do we want to be able to take expanded formulas, which again, those are our typical Lewis structures, and move to condensed and move to skeletal formulas because this is what we want to be able to draw most of the time. Mentally, we also want to be able to look at this guy and see all of these atoms in our head. Okay, so you're going to see problems on your test that are going to ask you to do some drawing, but you're also going to be able to just answer questions where maybe I'll point to a specific atom, like that carbon, and I'll say, how many hydrogens are on that carbon? And you'd have to mentally work backwards to this condensed structure and then this expanded structure to say, okay, there are 3 carbon atoms and 1 hydrogen atom bonded to that carbon. Some things that we'll just see, and you'll see a lot in organic chemistry, just different representations, not anything you need to draw, but just understanding that ball and stick models are really helpful for helping us visualize sort of what a molecular structure looks like. And that's where each atom is represented by a specific color ball. When we actually use models in organic chemistry, that's what they'll actually physically look like. But what we need to remember is that electrons, which surround these atoms, take up space. So a space-filling model really tells us the space that each of these atoms really takes up. So again, it looks really cluttered, but remember, there's not a lot of empty space in atoms or in molecules. It's actually taken up by electrons. All right. So one more kind of slide to go through here before we practice. And again, this is a slide that is present in its entirety, or there's like 3 parts to this picture that's present in its entirety on Blackboard. And I encourage you, this is not one obviously that we saw in Gen Chem 1, so I encourage you to kind of have this out and available as we go through problems today. So the first thing, and again, I'm just summarizing some stuff that was on our previous slide there that we discussed. This paper that you have here, this worksheet is going to allow us to work in 2 directions. And so that's what these arrows are going to be. We're going to talk about how we take Lewis structures and move to condensed and then move to skeletal, and then in the opposite direction. So first I'm just going to kind of remind us what each of these structures are, and then I'm going to go in the direction that takes something that we're familiar with, a Lewis structure, and how do we condense it and then write it into a skeletal structure. So right, this is a Lewis structure. So is this guy right here. I'm going to work with isopropyl alcohol. This is the active ingredient actually when you have rubbing alcohol. So this is what that chemical looks like. And so again, the advantage of a Lewis structure is that we basically, in drawing out every single atom and every single bond, we can see everything there very easily. Okay, so we clearly know everything that's present. The huge disadvantage, though, is it takes a lot of time to draw this molecule. So I'm going to have 3 sort of analogies that I have here. I equate this to printing. Printing takes a long time to do, but it's very neat. No one's going to misinterpret what's written there because it's very easy to see every single letter and know every single piece of what you're writing. Same is true for Lewis structures. Okay, but again, we're going to start moving towards making these skeletal structures. For the first step, we're actually going to condense structures. So remember, what that means is taking and collapsing any carbon-hydrogen bonds down and not writing this as separate bonds, but we're going to write this as a carbon with 3 hydrogens. So that's what we have right here. I also tend to eliminate this bond as well. So we're not going to eliminate the actual atoms that we have there. We're just eliminating the lines that we're drawing between them. Okay, so in this case, we're going to have all of these collapse to CH3, CH, CH3. And in this example, I still actually draw that OH group. I draw it going up there. I'm just going to show you here and highlight another way that you could draw this molecule that's still technically a condensed structure, and it's a way that we're going to tend to see things because it's easy to do when you're using a computer or a word processing program. So again, that's writing CH3, and then I'm going to write this CH, and then in parentheses, I'm going to write OH. So anytime you see something written in parentheses, that means it belongs to the carbon atom that's immediately preceding it. So this is another way to draw this guy as a condensed structure. And why this is even better or easier is if I'm typing something on my computer, I can just type this all on one line. So again, that's an advantage of that. So again, we still see lots of information. Every single atom is still going to be shown in a condensed structure, but we save a lot of time by not drawing all the bonds. It allows me to easily type things into a word processing document. Again, and it's one of these things that's a nice compromise between information and time. So I kind of equate this to thinking about cursive, right? Cursive's faster to write than printing, but you still have all the same information there. It's not like you got rid of some letters or had anything that was sort of abbreviated. It's just quicker to do, but still provides all of the information you need. So again, here's the directions for sort of what we did here. We collapsed all of our carbon-hydrogen and carbon-carbon bonds. So we merged all these atoms together. We didn't show the lines for bonding. We drew any of the carbon atoms that were part of our main line, kind of as they appear from left to right. And again, we drew here bonds as what I'm calling dangles, okay? But we could also collapse these atoms in dangles, and we could even collapse the dangles and put them part of the main line by putting them in parentheses. Okay, so again, we'll do some practice taking Lewis structures, drawing them as condensed structures, but the hardest thing is to probably think about how we would draw this as a skeletal structure. And that has to do with why these red dots are here. So when we want to be able to draw something as a condensed structure, and this is a strategy I'm going to introduce you to, and I encourage you to use it as long as you sort of need that scaffold. And how this works is when we are looking at a condensed structure, every time you have a carbon atom, I want you to draw a dot, okay? So drawing a dot is going to remind us where carbon atoms are. And why that's important is when we draw skeletal structures, the starting or the intersection of any line represents a carbon atom. So you can see here, here's my red dots for my 3 carbon atoms. Okay, so again, we draw dots for every carbon atom, and then we're going to draw a zigzag chain of dots for each carbon in that main line, and then we're going to add dots or atoms for any dangles. And I'm going to highlight here that when we have some of these dangles, if they are heteroatoms, we want to draw these out. So when we see skeletal structures, basically we are not going to see any carbon atoms or any hydrogen atoms unless they are part of a heteroatom. Okay? But if you think about starting with this starting structure, and if you were to practice and time yourself, draw this guy, then draw this guy, or even this guy for that matter, and then draw this last guy. Draw this guy here. Literally zigzag OH. How quick is that? Super quick to be able to draw skeletal structures. okay? But because we are eliminating information from our visible site, we have to make sure that we do not draw more than 4 bonds to carbon. It's a very common mistake that students make when we're learning to do this, that you'll draw more than 4 bonds to carbon. Okay, so again, advantages of this, we can draw things really quickly. And only non-carbon and hydrogen atoms are really shown, those heteroatoms. Now, again, this hydrogen is shown because it's bonded to a heteroatom, so that's why we have that guy. So again, disadvantage, a lot of the structure is really invisible. We have to be able to assume and mentally see some information that's not there. So again, that can take some practice, okay? So I liken this to thinking about learning how to write shorthand, right? Unless you understand what this means, it's a lot of nonsense. So again, looking at this guy, we didn't talk about what this guy looked like beforehand. So you might look at this guy and be like, I have no idea what that is. So I'm going to take a second here and let's work backwards, okay? So how would you actually take a skeletal structure and either directly or at least mentally be able to see what's there? Again, I can draw these red dots in here anytime there's an end of a line or an intersection of a line. Those represent carbon atoms. So I can see that I've got 1, 2, 3, 4 carbon atoms in this molecule. So I'm going to work backwards here. There's my 4 carbon atoms, 1, 2, 3, 4. So now, again, working backwards here, draw dots for every carbon atom in the skeleton structure. And so here's my dots, and those each represent carbon atoms. I'm going to draw a straight chain of dots for the longest chain of carbon atoms that I see, and then dangles for each carbon atom and other groups. So again, here was my longest straight chain of carbon atoms. 3. So that's why I drew 3 carbon atoms across here, and then I had 1 that dangled off. Now look here, I can see that 2 carbon atoms were double bonded, so I'm going to draw a double bond in here. Now I have to make sure I only have 4 things bonded to each carbon atom. So imagine if I hadn't yet drawn these hydrogen atoms in yet. Let's go ahead and just do that so you can see that. I would have drawn a dot, dot, dot. That's a carbon, carbon, carbon. I would have connected those and then to this dangly carbon, and then I would have made that a double bond. Okay, now I need to make sure I count to 4. This guy already has 4 bonds to it, so there's no additional hydrogens that I'm going to draw there. This guy only has 2 bonds, so I'm going to add 2 hydrogens. This guy only has 1 bond. I add 3 hydrogens. Remember, we're doing condensed structures here, so I'm not drawing out all my bonds. This guy, again, only has 1 bond, so I give him 3 hydrogens. Okay? Now, one of the things you could consider doing too, if I wanted to draw this all on the same line, I'm going to collapse these 2 groups together, put them on the same line. There's 2 of them, and they're bonded to that carbon. So this is kind of the only exception of the parentheses rule, is if there's a dangle kind of on the first carbon, then you would actually draw it first there. So this carbon is bonded to 2 CH3 groups, and then doubly bonded to that carbon. That's its 4 things. All right, so if we wanted to go and expand this out even further, right now we've got everything there. We can see all the atoms. We just need to expand out the bonds. Okay, so again, carbon, this CH3, we're going to write out all those carbon-hydrogen bonds, write out all those carbon-hydrogen bonds, and then write out those carbon-hydrogen bonds. So again, sometimes in our condensed structure, we are going to show bonds if they're double or triple bonds, because those are kind of unique. Okay, but we're not going to draw single bonds, and especially not drawing bonds to hydrogen. All right, so that was a lot that's there. So let's take some time and run through and do some practice. Again, it's going to be a little bit of a longer video here. I want to make sure with this new skill, I show you enough examples to practice, and then we'll probably work through homework when we have our face-to-face meeting here. All right. So let's go through and we'll practice. This is the sample problem that's in your textbook. There's actually very few sample problems we're going to be doing from the textbook just because they take a much deeper dive on certain areas that we're not going to be going into. So this first problem has us drawing different isomers. So we want to draw different isomers. So same parts, but drawn in different ways. And the best strategy I can give you for this kind of a problem is to be systematic for it. So again, let's call this A, B, and C here for these different parts. For A, we want to draw something that has 6 carbon atoms, no multiple bonds, and no rings. Okay, and we're going to draw these as skeletal structures too. I don't want to waste the time trying to draw these as Lewis structures. All right, so here's a strategy for drawing things with skeletal structures is when you put your pen down, you want to say the number 1 because when you put your pen down, you've drawn 1 carbon. And I'm going to draw these right now, not just drawing zigzags. I'm going to draw zigzags with my dots so we can make sure we easily see carbon atoms. So watch how I do this here. I've got 1, 2, 3, 4, 5, 6. So I drew 6 carbon atoms all in a row there. Okay? So again, that's our first molecule. Now, if you want, try, practice. Draw this out as it would be a condensed structure. And if you even want to take the time and draw it back out as a Lewis structure, go ahead. I'm not going to do that here. I'm going to move on and I'm going to say, let me draw another isomer of this. Now, drawing something that looks like this, 1, 2, 3, 4, 5, 6, that's still the same thing. All I did was sort of change the direction that one of those carbon atoms is pointing in. So this is the same thing. So that's not a new molecule. So I actually can't take 6 things, if I only have 6 things that are in a straight line and rearrange them in any way and make anything different because they're all carbon atoms. So my next thing to do is say, all right, let's make 1 chain shorter. So I'm going to make 5 in a row. 1, 2, 3, 4, 5. And now I can't dangle something off the first or the last carbon because that would still make the same thing that I started with. So I'm going to dangle 1 carbon off here. That's a new molecule. Another way to think about this is as I'm drawing, notice here when I drew this first guy, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. With this guy, I didn't have to lift my pen. That's an indication that that was the same guy. Watch for this guy. 1, 2, 3, 4, 5. I had to lift up my pen. That tells me that it's one of those constitutional isomers. I have things connected in different ways. All right, let's see if we can draw another isomer that has 5. 1, 2, 3, 4, 5. What if I were to put this guy down the middle? That would be a new molecule. And now I'm really on a roll, so I'm just going to keep going here. 1, 2, 3, 4, 5. Let's do this guy. Oh, whoops. Do you guys see that this guy is the same as this one? One of the things we need to be able to do is kind of mentally rotate things in space. If I rotate this guy 180 degrees, I get that same guy. So that's not a new species. That's the same. So I've kind of exhausted my 5 carbon chains. All right, let's go to 4. 1, 2, 3, 4. All right, what if I were to do this, 5, and 6? That looks like something new. Let's try this. 1, 2, 3, 4, 5, 6. That's a new guy. All right, what if I were to do this? 1, 2, 3, 4, 5, 6. I made another one, right? Oh, does everybody see? These guys are the same. So a lot of this is some trial and error, kind of trying to figure out how many different isomers I could make. So this is kind of like a puzzle, kind of trying to figure out how many different ways could I sort of piece these things together. All right, so let's do B and C here. I've got 4 carbon atoms and I want to have 1 double bond and no rings. All right, so 4 carbon atoms. Let's put them all in a row. 1, 2, 3, 4. Okay, I can put a double bond between the first and the second one. All right, 1, 2, 3, 4. All right, double bond between the second and the third. Oh, 1, 2, 3, 4. Oh, wait. These guys are the same, right? So that's not a new one. All right, can I make something? Remember, let's take this same pattern. Let's make something with has 3 carbons, and then I'll kind of make one guy up here. I guess I'm seeing some symmetry here, so it probably doesn't matter where I put my double bond, because whether I put it where I just put it, or I put it here, or I put it here, those are all going to be the same thing. All right, I can't think of any other combinations here, so this guy is going to have 3 possible isomers. All right, 4 carbon atoms, no multiple bonds, 1 ring. All right, so if I have 4 dots that I'm essentially going to be making in a ring, I guess that makes a square, right? Okay, that's actually what we'd call a cyclobutane ring. Again, we're not going to worry about naming things, but that's what that guy is. All right, can I make a shape that only has not 4 vertices, but 3 vertices? Oh yeah, that's a triangle. Okay, I can make that, and that's 3 carbon atoms. That means I still have 1 that I can put outside there. All right, so this guy only has 2. All right, so a lot of this is just sort of, I don't know, playing with like pieces and permutations and combinations. It's kind of like a puzzle. All right, the last little piece to kind of highlight here, and another skill to sort of practice, is there's one more kind of isomer we can talk about. So this was what we call I should say there's 2 more kinds of isomers. This is a stereoisomer, what we have here, stereoisomer, okay? So this is actually going to have the same molecular formula, or I'm sorry, constitutional isomers have the same molecular formula, but we're going to have different groups in space. We're going to physically kind of have different groups in different spaces. This stereoisomer, which is also called an optical isomer, I should indicate that these are referring to the same thing. So stereoisomers are optical isomers. These are words describing the same thing. These are mirror images of one another, but again, they're not the same thing. If you want a great example of this, think about your hands, okay? If you look at your hands and you have the palms of your hands sort of facing each other, they are mirror images of one another, okay? But you can't superimpose them, right? If you have a right-handed glove and a left-handed glove, that's specific for that hand, okay? But there's lots of parts that are the same with them, right? Your fingers and your thumb are all connected in the same spots, but they're mirror images of one another. And this can be the same for molecules, okay? So a term I want you to know is a chiral center. This is a hard K. It's not chiral, it's a chiral center. So a chiral center, remembering that carbon, this is a carbon atom. Carbon atoms are shown in black in this ball and stick model. Chiral centers are carbon atoms that are bonded to 4 things. Carbon's always bonded to 4 things, but 4 different things. If we have a carbon atom that's bonded to 4 different things, that creates what's called a chiral center. And that's really important when we think about how molecules interact in your body, how drugs interact, how your own biological molecules interact. It's super important, okay? All that I want you to be able to do is, if you were looking at a structure of a molecule, for you to be able to tell me and circle, this is a chiral center. That's a carbon atom that has 4 different things attached to it. Okay, so we're going to look at some examples of that when we do our practice problems. Last kind of isomer, okay, are geometric isomers. So these happen when we have double bonds. Okay, so this was actually one of the examples that we drew back here when we were kind of practicing our problems. We had this guy here. So one of the things that's unique about that guy is, and again, here we're looking at a condensed structure and then a skeletal structure. We could have kind of our main chain in sort of like a U shape here, which is what we have here. Or we could have it in this zigzag pattern, which is kind of what we drew over here. It was in the zigzag pattern. These are different from one another and they do not interconvert. Okay, there is not rotation about that double bond. Let me actually put that in real pen here. We do not rotate about double bonds. So we cannot interconvert these. And they have specific names. I do want you to know these names. It's just these parts that are highlighted here. Cis means same. So we have our big groups on the same side. Or you could think about it as the hydrogens on the same side. Okay? Trans means across. So in this case, we have our big groups across from one another. Okay? So, skills for you to have is if you're looking at a molecule that has double bonds, I want you to be able to tell me, is that a cis double bond or a trans double bond? If you're looking at a molecule and it has a carbon atom with 4 different things, you would say, Dr. Parenti, that is a chiral center. Okay, so 2 kinds of isomers I want you to be able to recognize. So that's kind of it for what we're learning about in this first lecture. So lots of review. We have to make sure that we're very competent in drawing structures, because then we build on that with the special kind of ways we draw organic molecules. And then again, we just went through kind of how we think about drawing isomers. So if we were given, for example, a molecular formula, we could draw a lot of different kinds of representations, structures, using those same building blocks. Okay? So what I want to do is just spend a little bit of time here practicing. So again, this worksheet is available online. I encourage you to kind of get it down and write these out or print that out so that you have the ability to practice these. Again, what I'm going to do is for each of these, I'm actually going to, in the video, sort of walk through it, because this is one of those skills that it actually is a, hey, I got to see this in motion. I can't just see the static solution and sort of talk about it. We actually have to be a situation where we are kind of seeing it worked out. So we're going to do that. But I encourage you, maybe try these a little bit first on your own. See if you can kind of work through them. The first skill that we're going to do is actually taking a condensed structure and making it into a skeletal structure. So again, if you want to pause the video right now and try a couple of these on your own, go ahead and pause the video, and then I will work through these. All right, so remember, when we take a condensed structure, we're going to draw into a skeletal structure. The first thing I want to do is I'm going to mark down, and let me do this in red here so we can see this better. I'm going to put dots where all of my carbon atoms are here, okay? Notice I don't want to put a dot here. This is in parentheses, so that's not going to be part of a main chain. So I'm going to put dots together here. This guy's a little bit weird. I'm actually going to draw out what this guy looks like. I don't like that I left this way here. This looks like this. This is not an uncommon way to show a CH2CH3 group, but because it can get confusing, I want to make sure to highlight there. All right, so that's actually going to be 2 dots. All right, so let me count up my dots that I have here. I've got 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5 dots. So 5 dots means I'm going to do a zigzag with 5 dots. 1, 2, 3, 4, 5. Okay, now I have to take anything that was in parentheses, and that belongs to the carbon right before it. So I'm going to put an OH group on my second carbon there. OH. Now I've got a CH3 group on my third carbon there. So I'm going to put CH3. So one of the things I want to highlight, right, is maybe somebody would have done this. Watch this guy. You would have done, okay, I've got an OH and then I've got a CH3. Okay. That's not necessarily wrong. You connected everything in the same space, but this is very crowded. So we tend to alternate. The reason we do this zigzag is we give everything as much room as possible. So in this case, we're going to alternate the sides that things go. That just gives everything the most room, not only for your pencil when you're drawing, but that's actually how it looks in realistic three-dimensional space. So here's the answer for this first guy. All right, let's go to our second guy here. All right, so I have no parentheses here, so I don't have anything that's a more than one atom as a dangle, but I have to make sure here that I recognize, ooh, I've got a chlorine atom there. Now, you wouldn't put that in parentheses because it's a single atom, but I kind of have to recognize that that's going to be a dangle, and it belongs to the carbon before it. Belongs to the carbon before it, okay? And then I've got this carbon nitrogen, okay? We would have seen that as a cyanide group when we did our Gen Chem stuff with that being kind of an ion, but as we're going to learn in our functional group, we can call that a nitrile, or we can call it a cyano group. All right, but that's for next class. All right, so let's go through and figure out our main chain. I've got 1, 2. Make sure you don't mark that carbon. That's a chlorine. That's a Cl. 3, 4, 5, 6. All right, so I'm going to draw a zigzag with 6. 1, 2, 3, 4, 5, 6. All right. Now, this chlorine atom, this guy right here, belongs to the second carbon. So I'm going to put that there. I've got another chlorine atom here. So this actually belongs to my third carbon atom. I'm going to put that guy there. Oh, look at, I've got, and let me actually go through and do this just so that we can make sure, because things can get so confusing here when you're looking at all of this together. I'm going to kind of highlight here things that are not carbon and hydrogen. There's an oxygen atom that's in there. So that oxygen atom is actually bonded to that fourth carbon atom. So I've got an oxygen. And notice it doesn't have anything else with it. It's just that oxygen. For a couple of reasons, that's going to tell me that that oxygen is double bonded there. Again, I could see this, right? If I look at the carbon atom that it's bonded to, so again, let's do this. This oxygen belongs to that carbon atom. That carbon atom is bonded to another carbon atom and another carbon atom, and it doesn't have a hydrogen with it. So that must mean that this guy is a carbon that's doubly bonded to that oxygen. All right, so then I've got this carbon atom, which is that guy. There's 2 hydrogens that are there. And here's my last carbon atom. All right, so we've got it bonded to a nitrogen. So one of the things here that I can look at, I can say, all right, this carbon atom right here is bonded to this guy. It has no hydrogens with it. So the only other thing that it's bonded to is a nitrogen. So if I've got carbon with only one other bond, that must mean it's triple bonded to that nitrogen. And I'm going to do this like this, and then we're going to talk about why we see it like that. remember, if we've got a carbon atom, this was a challenging one to kind of come second out of the gate here. If we've got this carbon atom here, let's do some review. This carbon atom is bonded to only 2 other atoms. So I would say that the hybridization of this is sp. Yep, we got a lot that we got to review from Gen Chem 1. sp hybridization means I am linear. That's why I drew that guy the way I did. Okay? Wow, there was a lot in that guy. So if you need to, go back and sort of rewatch and review this guy. But that is what a correct skeletal structure will look like for this guy. All right, let's do another one here. All right, we've got 1 carbon, 2 carbons, 3 carbons. Let's go through and we're going to highlight here. We've got 2 oxygen atoms there. This guy, and then we've actually got, I'm going to draw this guy out again. We've got 2 of those. So I'm going to make one of them be a dangle, and then one of them is going to be in my straight chain. All right, so let's see what we've got here. I've got 1, 2, 3, 4, 5, 6 carbon atoms in a row. All right, so let's do that with my zigzags. 1, 2, 3, 4, 5, 6. All right. These oxygens belong to that 3rd guy that we have there. One of the things I'm going to realize is I can't put 2 oxygens on that carbon. I'm going to actually have to slip one of those oxygens in. Okay? And you'll start recognizing patterns as we see things here. This is going to be a carbon doubly bonded to an oxygen, bonded singly to a bridging oxygen. So that's what that guy's going to look like. So I'm going to have to correct this. Off of my 3rd carbon atom, I'm going to have an oxygen atom. That oxygen, one of those oxygen atoms is actually going to be in my line. All right, and then I'm going to have my 4th, 5th, and 6th atoms there, carbon atoms. All right, so let's go back here. On that 3rd carbon atom, that's where I had a double bond to an oxygen and then a single bond to an oxygen. Okay, and then what I'm going to have is here's this carbon atom, and then on that carbon atom is where I'm going to have this one guy that's a dangle belong there. Wow, there's a lot to this problem. So this kind of comes off as a dangle, dangle. Wow, there was a lot to that problem. That was intense. Okay, but let's go through and let's just check. I've got CH3, CH2. That's what I've got there. Then I've got a carbon doubly bonded to an oxygen and then singly bonded to an oxygen. I got that piece right there. Then I'm going to have a carbon that's bonded to a hydrogen. That's right there. And then 2 of these things. Oh yeah, I see how 2 of those things are attached now. Okay. All right. I see that one now. All right. Let's do one more here. Okay. And then what I think I'll do is I will save the next set to be ones that we'll go through and practice in class. All right. So again, here I've got some stuff in parentheses, but not because it belongs to a guy previous. This just has to do with there being repetition. So this is repetition. Sometimes, particularly if it's CH2 groups, we're going to have a bunch of them in a row. And so we need to sort of recognize that we're going to have 2 of those in a row. So I'm going to have 1 here, then I'm going to have 2, 3. Those are 2 carbons together. 1, 2, 3, 4. This guy actually belongs as a dangle to that guy, so he's not part of my main chain. And then 5. Okay, so I'm going to have 1, 2, 3, 4, 5 carbons. And then I'm going to have this group that I'm going to have to put on the end. COOH. And the more of these you start doing, you'll kind of start recognizing stuff. All right, so I need to have, let's count again, 1, 2, 3, 4, 5 carbons in a row. 1, 2, 3, 4. 5 carbons in a row. All right, so these two that were right there, that's this guy and this guy. So I've got this one here, 2, 3, 2, 3. And then on my fourth guy, that's where I'm going to have this. So my fourth one, I'm just going to put a line up because that's a carbon atom there. That's a CH3 group. And then on my terminal carbon, all right, if I've got to have that carbon be bonded to an oxygen and then an OH, okay, the only way I can do that is it's bonded to an OH and then, oh, that must be what this group looks like. Okay, this is a C double bond O, OH. So one of the things we're going to start doing is recognizing these are functional groups, and this is what they look like. Again, you don't need to know this for today, but next class we'll learn this is an ester functional group. This is a carboxylic acid functional group, and this is what they look like in a condensed structure and what they look like in a skeletal structure. So we'll start sort of recognizing these pieces. All right, so we've spent a lot of time already sort of doing some practice in the video here. I'm going to pause and let us work on these ones when we have our face-to-face meeting in class. But again, here's another way that we need to be able to practice this. Okay, and this one is more of a mental exercise than anything that you realistically, pragmatically do in real life. What we want to be able to do is make sure that we can get to be able to do this mentally. We do this less physically than we do actually on paper here. So again, I'm going to just kind of go through these. I'm just going to draw them as condensed formulas, taking them all the way out to Lewis structures just takes way too long. But let's see if we can do this. All right, we'll practice a couple of these here. Every place that I've got the end of a line or an intersection of a line represents a carbon atom. So again, I'm going to string those together. Carbon, 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 carbon. All right, now I have to make sure that I add enough hydrogens so that every carbon is bonded to 4 things. So one of the patterns that you'll start recognizing is carbons that are at the end are going to be CH3s. Carbons that are in the middle and not bonded to anything else are going to be CH2s. So this becomes a CH3, CH2. Look at that trick there that I did there with my bonds. They became H's. CH2, CH2, CH3. That is the condensed formula for that guy. And again, I could collapse these down if I wanted. I could write this as CH3, and then I've got 4 CH2 groups together, and then a CH3. That's a way to even make it a little bit more simple. All right, a little bit more quickly now. These ones I think are easier to do, but again, we want to be able to get it so we see it sort of mentally. I'm going to just kind of try to draw this one out just by kind of visually seeing it and saying it. So I've got CH3 at the end, right? So I'm going to kind of walk through. Actually, let me walk through with my laser pointer here and then I'll write it. CH3, CH2, CH with parentheses OH, CH2, CH2, CH3. Okay, so I'm going to say it again as we kind of write it out here. CH3 at the end, then CH2. Then I've got a carbon that's bonded to a hydrogen, and then the dangle that belongs to it is an OH. And then I've got another CH2, CH2, CH3. All right, let's check out this guy. This guy's a ring. So I got to draw some carbons in a ring here. So learning how to draw your shapes from hexagons and pentagons and so forth is really important. So I've got carbon doubly bonded to oxygen. These two guys are doubly bonded. So again, I got to go and make sure everybody gets enough hydrogens. So this is going to be H2, H2, H2. Oh, these guys each only get one. And then that guy, that first guy, nothing else to that, right? No hydrogens on that carbon. All right, let's do my last one here. Got another hexagon I'm going to be drawing here with my carbons. All right, I'm going to have an OH group here. This is a CH3. Anytime you just see a line is just going to be a CH3 group. All right, this one doesn't have any double bonds. So if I kind of go through here, I've got an H2, 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 H2. Okay, each of these guys has one H. So one kind of problem that you might see on a test is I might ask you how many hydrogens are bonded to that carbon? Or I might say, how many hydrogens are in this whole molecule? And you'd have to either mentally see or physically draw so that you could count the number of hydrogen atoms that you have. Okay? So that sort of wraps up, and again, we'll go through the rest of this practice problem, kind of running through how we would actually take this and put this into kind of a more condensed structure, being able to sort of count things. So we'll do those last two pieces on our on these practice problems in class, and then we'll still probably have time to work through your homework problems.